Hello, everybody, and welcome to more statistics. Tonight or today in this class, we're going to talk about measures of dispersion. And the purpose of measuring dispersion is to indicate how far from the mean the data is dispersed. So, is all of the data very close to the mean? Or is all of the data, or a lot of the data, spread far out from the mean? To illustrate, let's recall a couple of examples from our last lecture. Class 1, final exam grades, 10 students in the class. Whoa, everybody in the class got a 70. And the mean, arithmetic mean, final exam grade was 70. Now, how far away are these data values from the mean? They're not far at all. As a matter of fact, every single one of these data values equals the mean. So these data values aren't dispersed at all. Every single one of these things equals the mean. Now compare this with class 2. 100, 100, 0, 100, 100, 100, 0, 100, 100, 0. 7 100s and 3 zeros. The arithmetic mean final exam grade was a 70. Both classes had a mean final exam grade of 70. But look at these test scores in relation to the arithmetic mean. The closest test score to the arithmetic mean is 100, and that's 30 units away. Some of the test scores, like 0, are 70 units away from the mean. So if we were given only the mean, we wouldn't know. Well, let's see. Did they all do about the same? All of the students? Not too good, not too bad. Average, typical students. They all got 70. Would we assume that, or would we assume, well, maybe some got 70, some got 80, some got 60? Or would we assume a bunch of hundreds and a few zeros? Just looking at the mean, we don't know whether all the test scores are very close to the mean, like in this case, or whether all of the test scores are very far away from the mean in this case. So in addition to computing the arithmetic mean, which we used to know as, quote, the average, we also want to measure how far away from the mean these data values are. And there are a couple of different ways that we can do this. But the first measure of dispersion is the range. The range of a set of data is computed by taking the greatest data value and subtracting the least data value. Well, what would the range be here? Greatest minus least. And of these 10 scores, which score is the greatest? The highest score, the greatest score is 70. And of these 10 data values, what's the least data value? 70 again. So our range equals 0. And I'll give you a hint. The smaller the range, the less the data values are dispersed. The range is 0 here. The mean is 70 and the range is 0. That tells the story completely. All of the data values have to be equal to the mean. Okay, let's do the same thing here. The range of these data values. Whoops. Range equals greatest minus least. And the greatest data value is 100. It occurs 7 times. The least data value is 0. It occurs 3 times. So the range here is 100. In this set of data, the mean is 70. The range is 100, and that's as big as the range can possibly be. The highest score on an exam is 100. The lowest score is a 0. So if we see that the range is 100, that means at least one of the final exam grades had to be 100, and another one had to be 0. Now, that could mean a bunch of things. It could mean that there was one really good student in the class who got 100, and one rather poor student in the class who got a 0. And maybe all the rest were average, who knows. But we have an idea that at least one student did very well and another student did poorly because the range is so great. Now let's look at another measure of dispersion. A little bit more insightful measure of the data from the mean is the standard deviation, and typically we represent it as little s. This is the formula for it. We take the sum of the square of each data value minus the mean and divide by n minus 1 and do the square root of all of that. Pretty complicated process. Let's do it with this set of data. We have 6 data values. And notice something. In order to use this formula, we need to compute the mean first. So first thing, x bar, and we just add these things up and divide by the number of data values. And let's see, we have 30, 30, 60, 78 over 6, and that's going to give us 13. Okay. X bar equals 13. Now let me erase some of the board because we're going to need a lot of space. Okay? Our mean x bar is 13. These are our data values. n equals 6. We have 1, 2, 3, 4, 5, 6 data values. Here is our formula. Whoops, 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 whoops. Forgive me, this is not x bar. This is the formula for the standard deviation S. X bar is 13. The standard deviation S is this monstrosity. And what this says is, for each data value x, we have to subtract the mean from x and square it. And then we have to take that value and add it up. So let's do that. I'm going to draw a big fat square root here. For each data value, we have to take the data value minus the mean, 13, and square it. And then we add all of these up. Here's the first data value, 14. We take 14 minus the mean, 13, and square it. Then we go on to the next data value. We take this data value, 14, subtract the mean, 13, and we square it. And then we go to the next data value, 10, and from this data value, 10, we subtract the mean, 13, and we square it. Then we go to the next data value, 8, and from this data value, 8, we subtract the mean, x bar, which is 13, and square it. Then we go to the next data value, 16. From this data value, we subtract x bar, which is 13, and we square it. Then we go to the last data value, 16 again. From this data value, 16, we subtract x bar, which is 13, and we square it. And all of this goes over n minus 1, where n is the number of data values. N is 6. We have 6 data values. 1, 2, 3, 4, 5, 6. N is 6. On the bottom, we want n minus 1. So we're going to put 6 minus 1 here. Holy moly! 14 minus 13 is 1. 14 minus 13 is 1 again. 10 minus 13 is negative 3. And we square it. Then we do 8 minus 13, that's negative 5. And we square it. Then we have 16 minus 13, which is 3. And we square it. And we have 16 minus 13 again, which is 3. And we square that. And on the bottom we have 5. And this gives us, when we work everything out, 1 plus 1 plus 9 plus 25 plus 9 plus 9 all over 5. And let's see, what do we get? 20, 45, 54 over 5. And this turns out to be 10.8 under the square root. And I worked this out earlier, and when I did, I got 3.29 approximately. Standard deviation, S, is approximately 3.29 units. Before I erase all of what we just did, do you know why it is that we have to square this? If we didn't square this, some of these things would be positive, some of these things would be negative, and in the end, we'd wind up with 0. Let's see if that works. 1 plus 1 is 2, minus 3 is negative 1, minus 5 is negative 6, plus 3 is negative 3, plus 3 is 0. Yeah, see that? We're trying to measure how far the data values are, x, from the mean, but we have to square these things, otherwise the pluses and the minuses would even out, and in the end we'd get 0. So that's why we had to go to all of this trouble of squaring each difference between a data value and the mean. We had to take each difference of a data value and the mean and square them. And that would keep everything from canceling out. And then to compensate for the fact that pretty much we squared everything, we computed the square root after we added everything up. Now let's revisit, I think it was class number 2, maybe? Class number 2, I think so. Let's revisit class number 2. Okay, remember class number 2? Final exam scores, we had 7 100s, 3 zeros. The mean is 70. But none of those test scores is even remotely close to the mean. So let's compute the standard deviation of these test scores and see what the standard deviation tells us as far as how far from the mean these test scores are dispersed. Compute the standard deviation. And we have our formula. Square root of the sum of each test score x minus the mean x bar squared. So for each test value, we take the difference between the test value and the mean and we square it. And then we add these things up. And we divide by n minus 1, where n is the number of data values. By the way, do you remember how many data values there were? 10. Okay. So n equals 10. . . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 . 10 Now let's do this. The first data value is 100. The mean is 70. Second data value is 100. The mean is 70. The third data value is 0. The mean is 70. The fourth data value is 100 minus the mean, 70. And of course, we're squaring all of these differences. Holy moly, that's just 4. Okay, we continue in this fashion. 100 minus 70. 100 minus 70 squared. How many is that? 1, 2, 3, 4, 5, 6. Are we going to fit these things in? Yikes. Let's see. 0 minus 70 plus 100 minus 70. Okay, we got 8. 100 minus 70 and 0 minus 70. All over n minus 1. N is 10. Holy moly. Well, let's see. We only have 2 numbers to figure out. 100 minus 70 is 30. And 0 minus 70, negative 70. So let's see. What are we going to get? 70 squared plus 70. Nope. That's not right. 30 squared plus 30 squared plus negative 70 squared plus 30 squared plus 30 squared plus 30 squared. Okay, that's the first 6. And then we got negative 70 squared. And then we got 30 squared again twice. And then negative 70 squared. Excuse me. Holy moly. Give me a minute. I'm going to have to pull out the calculator and crank this out. Okay, darn near killed me, but I cranked this out. It comes out to be 48.3. The standard deviation is 48.3. And essentially what that means is on average, the data values are about 48.3 units from the mean. Not exactly, but good estimate. 48.3 is a good estimate of how far the data values on average are dispersed from the mean. Well, let's see. We did class 2. Let's do class 1 just for the sake of comparison. Here, the mean, 70. Students could have been all average, or we could have had some really good students, some really poor students. Who knows? But now that we see the standard deviation and we know these final exam scores are way over the place, all over the place. And so what that tells us is the average is 70, but we got some really good scores, some really poor scores. maybe some in the middle, who knows? Now let's do class 1 and see what their standard deviation is. Class number 1, final exam scores, everybody got a 70, and they were 10 of them. Now let's compute the standard deviation. The standard deviation, the square root of the sum of each data value minus the mean squared, all over n minus 1, where n is the number of data values. I don't know if I'm going to write all of these out or not. We take the first data value, 70, and we subtract the mean x bar, which is also 70, and square it. Then we take the next data value, which is 70, subtract the mean x bar, which is 70, and we square it. And we continue to do this for each of the data values. And all of the data values are the same. Well, notice something. 70 minus 70 is 0, and when we square it, we still get 0. What we're going to get is 0 over 9 square root, which is 0. And this tells us that there's no dispersion between the data values and the mean. Essentially, they're saying that each of the data values is equal to the mean. So this tells us a very accurate account of what happened on the final exam. The mean, 70, tells us part of the story. The standard deviation tells us the rest of the story. We put these two devices together, these two statistical tools, we put them together, they tell us a pretty accurate story of what happened on the final exam.